All right, let's go ahead and get started here. I'm going to have a few problems here on thermodynamics. I know we just introduced this in lecture, so it may be a pretty relatively new topic for you guys. We're going to go ahead and start working out some problems that you may see. Difficulty level would be the same as the exam. I know sometimes I try to do harder problems than the exam just because I want to get you guys thinking. And so if you can solve those problems, you can definitely solve the ones that are on the test. But I have made them a little more simpler, and you can expect the difficulty of these to be the same as your homework and your exam coming up on Thursday. So let's go ahead and jump right in with Gibbs' free energy problem. So we're looking to calculate the Gibbs' free energy change. I gave the chemical equation, I gave the standard entropy and the standard enthalpy. So delta H is enthalpy and delta S is entropy. Don't get those confused. So you want to think of chemistry 110 problems like a steak, almost. You work out the problem, you're cooking the steak, and then you want to garnish with your units. The units they always have to be correct, especially in this unit thermodynamics. You have to convert between kilojoules, joules, watch for moles, watch for grams. You always want to make sure that your garnish on your steak is correct. So if we're looking for kilojoules per mole, that's your garnish. Toss it on, serve the plate, you're good to go. That's how I think of chemistry problems. You can think of them other ways, but makes sense to me. So let's think about that as we're going through here. We're making a steak. So we're given the chemical equation. We're solving for delta G standard. Well, we know that delta G standard is equal to delta H standard minus T delta S standard, right? We learned that equation on Wednesday's lecture. This is the simple Gibbs free energy problem. Again, if my Gibbs free energy is standard, these all have to be standard, and we know standard is at 1 bar pressure, and we have 1 mole. So, well, the delta H is given to us, but be careful. It's in kilojoules. Remember, our garnish on the steak has kilojoules, so we got to watch for that. Temperature, we know it's standard, so it's 298.15, or if you just want 298, that's fine as well. Your answer won't be that much affected. So now here's where a lot of students would make a mistake. So we have an entropy of 508.9 joules per Kelvin. Well, I've already decided that my garnish on my steak is going to be in kilojoules. So when I'm working out and cooking the steak, it needs to have kilojoule units. So that as a kilojoule value is just 0.5089 kilojoules per degree Kelvin, right? 508.9 divided by 1,000 is just 0.5089. So now we solve this, and we get negative 1,044.3 kilojoules. If my delta G, or Gibbs free energy, is negative, what does that mean? Well, let's think about entropy. When my entropy last week unit, on last week's video, was positive, was that spontaneous or non-spontaneous? When the delta S of the universe was positive. If it was positive, we had a spontaneous change. Gibbs free energy is the exact opposite. When you have a negative, it's spontaneous. So in this case, this would be spontaneous because it's a negative delta G. So a follow-up question they may ask on the exam, or you may have seen on your homework actually as well, is what temperature would be needed to make this reaction non-spontaneous? So let's think about that. So temperature when this reaction becomes spontaneous, because we know it's spontaneous already, right? But we want to know exactly what temperature this whole reaction becomes spontaneous. So let's think about that. Temperature, if we relate it to our entropy equation, we know temperature is equal to delta H standard over delta S standard. Well, we have both of those values. We have negative 1196 and we have 0.5089. So now if I solve for temperature, I get negative 2350.2 degrees Kelvin. So basically, again, this would be a follow-up. I don't know if they would ask this, but it's something for sure to keep in mind. The temperature at what this whole reaction becomes spontaneous. We know already that's spontaneous because the negative delta G, once again, that's easy to see. But we want to know exactly what temperature, for laboratory purposes, this will become spontaneous. negative 2350.2 Kelvin. Really cold. So putting that in perspective, I mean, that's really cold. So very simple, straightforward problem. This is probably the easiest one of the three. I would expect most of you guys to get this right on the first try just because it's an application of delta G equals delta H minus T delta S. Watch your units, and then this would be above and beyond. Once again, I don't know if they would ask this, but it's something to keep in mind for sure for moving on. Okay, great. Moving on to the next question. This one's probably the hardest of the three that we're going to do today. So we're looking to calculate the delta H, the delta S of the system, and the delta G of the reaction. We're at 298 Kelvin. If you're not given a temperature, I would assume 298 Kelvin. We would probably give it to you, but if not, I would give it an assumption of 298 Kelvin. And then I gave you the delta H of formation, which is 54 kilojoules per mole. And I gave you the delta S of formation, which is 166 joules per Kelvin mole. So right away, I see my steak garnish is already off. I need this in kilojoules, but we'll worry about that later. And these are both formation values for methyl hydrazine. And then here's your equation. Sorry, I ran out of space. This is just a continuation. So I would encourage you to pause the video and try this one by yourself. It's a really good problem. If you can do this by yourself, you're doing well for thermodynamics. If not, if you're totally stuck, that's fine too. So let's look at the delta H of formation and the delta S of formation of each of our reaction components. So I'm just going to make almost like a little table. Delta H of formation, delta S of formation. It's not necessary to do on the test. You probably won't have this kind of time, but I'm doing this because I want you guys to see what exactly I'm doing to get my numbers. So we're going to lay out each reaction component. N2H3CH3. That is our methyl hydrazine. If you're confused on how I got that to be methyl hydrazine, I mean, you can pick it out. CO2, N2, H2O definitely aren't methyl hydrazine. This is methyl hydrazine because CH3, you'll learn in organic chemistry 1 that CH3 means methyl group. So we can already pick out that this is the methyl hydrazine. If you didn't know, you could probably take a guess, but going back to the casino is not always the best option when you're guessing. The 50-50 shot does not pay off. Okay, so now I have all of my reaction components. Let's think about what my delta H and my delta S is for each. Well, I'm given these two values, right? I'm given the ones for methyl hydrazine, 54 and 166. Well, we know 1 mole of reaction makes 4 moles, right, of methyl hydrazine. Every time this reaction goes through once, we have 4 equivalents of methyl hydrazine. Does that make sense? Every time this reaction happens once, I have 4 moles of methyl hydrazine being made. So looking forward, these are all tabulated values. We would probably give them to you on an exam, especially a problem of this depth. So I'm just going to fill them in for you. Again, I'm not solving for these. I'm just getting these off the internet. We would not ask you to solve for this many reaction equivalents in one problem because, once again, I just don't think you have that kind of time on the test to do that. I don't think I could do that in under 5 minutes. That would take a lot of math. So we have our tabulated values now. And we know that delta G is equal to delta H minus T delta S. That's kind of the general equation we're using for almost all thermodynamic problems, it seems like. Up to electrochemistry, you're probably going to be using this equation almost everywhere. So get to know it pretty well. Well, we know that delta H and delta S of formation are just products minus reactants, right? Anytime I see a delta of formation, I know it's products minus reactants. Well, luckily, I know all of my delta H's for my products and my reactants, and I know all my delta S's for my products and my reactants. So why don't I solve for each delta H and delta S individually and then encompass that into my equation? Let's give that a shot, see where that gets us. So delta H of reaction is equal to products minus reactants. What's my first product? H2O. I have 12 equivalents of H2O, so I do 12 times its delta H, negative 286, plus I have 9 equivalents of nitrogen, 0, plus I have 4 equivalents of carbon dioxide, 4 times, sorry I missed a parentheses there, but it's okay, negative 393.5, close parentheses. This is my products, minus reactants. Well, what are my 2 reactants? N2O4. I have 5 equivalents of N2O4, and they're each at negative 19.58, plus 4 methyl hydrazines. 4 times 54. So now I have products minus reactants, and they're all delta H. So the delta H of reaction is equal to negative 5121.7 kilojoules per mole. Again, don't get lost in the sauce here. You want to make sure that you have products minus reactants. The only reason I'm adding here is because I'm adding all the products together minus all of the reactants added together. You add everything together for the products, add everything together for the reactants, and then subtract the 2, and you get a total delta H. I feel like a lot of students will start subtracting here. I don't know why, but that's why I add these brackets to make it more clear to myself when I'm working it out that, okay, this is my products and bracket, this is my reactants and bracket. So I know what I'm doing. Just a good way to stay organized when you're working longer problems. So I'm looking for the delta S of the reaction. Well, we know it's just products minus reactants, so we're going to do the exact same thing, except we're going to use the second row here with delta S of formation values. So I have, once again, 12 times 188.8 plus 9 times 191.5 plus 4 times 213.8. Sorry, I'm writing small. I just want to fit this. So that's my products and bracket. And then reactants, minus 5 times 209.2 plus 4 times 166 and bracket. Solve for delta S of reaction, and you should have gotten 3134.3 joules per mole Kelvin. So now I have delta H, I have delta S, I can solve for delta G, right? Just be careful on the units. So my delta G of the reaction is equal to, well, we know it's delta H minus T delta S, so let's fill in our values. Our delta H was negative 5121.7 kilojoules per mole, minus, well, my temperature, it was given, but again, we can always assume 298 if said otherwise. What is significant here? 3134.3 joules per mole Kelvin. Well, I don't want it in joules, right? I want it in kilojoules because my delta H was in kilojoules. So what do? I divide this by 1,000. So we'd have 0.3134.3 kilojoules per mole Kelvin. Now everything is in kilojoules and I'm good to work my reaction out. So delta G of the reaction I got to be around negative 6,055.72 kilojoules per mole. Okay. If we want to find each delta H, delta S, delta G of the system. For each component, we can do that. I was just looking for the delta G of the reaction. You can find the delta G per mole of constituent. So for example, if we were doing the delta G of, we'll just stick with methyl hydrazine. So we know we have 4 moles of methyl hydrazine formed, right? So if we have 4 moles of methyl hydrazine, and this is negative 6055.72 kilojoules per mole, we can just divide this by 4. I'll do that actually. So if we divide this by 4 moles, we get negative 1513.9 kilojoules. That would be the delta G per 1 mole. Because remember, we had 4 moles being used up of our methyl hydrazine. So if I divide this by 4 moles, the moles cancel, and I get a kilojoule value here. This would be per reaction quotient or per reaction component, and this negative 6,000 number would be our delta G of the reaction. Just something to keep in mind on an exam. If they were to ask you for the delta G of the reaction versus the delta G for an individual component. That's how you would go about solving. Again, it's just stoichiometry, application of Chem 109 concepts. We see that a lot in 110, I feel like. Okay, and then the last problem that we're going to do today, it's a very common problem. You'll see a lot of these. And there's quite a bit on your homework that involve these kind of, almost looks like mechanisms for, in this case, hemoglobin. HB means hemoglobin. For those of you who are life science people, you'll see hemoglobin quite a bit, because we know hemoglobin is the iron-containing molecule that carries oxygen to your blood and tissues, and it's really important, especially as you get into exercise physiology. The aspects of hemoglobin are actually really interesting, what it does for your body, but we won't get into that. We're not lecturing on hemoglobin today. We're looking at Gibbs's free energy. It's a little different. So given the following data, determine the Gibbs's free energy. So looking back from Chem 109, we had something called Hess's law. If you remember from Chem 109, Hess's law, we basically flipped and multiplied reactions together to get the overall reaction, which is this. So if I want to alter these reactions to get that, well, let's take a look at what we have. Let's go equation by equation. So I have HbO2 plus CO goes to HbCO plus O2. What do we notice is significant? Let's look at the first reaction. So I have HbCO on the products. HbCO is on the products. Great. I have CO, one CO here. Great. Hemoglobin, Hb. I don't see singular hemoglobin anywhere in this reaction. So that's something to consider. We can't flip anything now. Let's look at the second reaction. O2 is a product. Oxygen is a diatomic element, it is a product. In this case, it's a reactant. If we want to get this over here, what do? Well, we just flip it. So now we have HbO2 goes to Hb plus O2. And if we flip the reaction, what happens to the sign of the delta G? Whenever you flip it, it's just like K back in Hess's law. This becomes a positive 75 kilojoules. And I didn't change the first reaction, so I'm going to go ahead and write it below. And the delta G for this obviously won't change because we didn't do anything to the reaction. So now what can we cancel? Well, Hb is here, Hb is here. I need HbO2 and CO on the reactants. I have HbO2 and CO on the reactants. I need HbCO and O2. I have HbCO and O2. So the delta G total, I would just add these together, right? And we know that's a lot easier than the math we've done previously. We know the delta G standard is equal to negative 5 kilojoules. Again, it's just an application of Hess's law. You're just flipping and altering equations to get the correct answer. There's no extra math necessary. There's no delta H. There's no T, delta S. I guess I can apply this for a follow-up question. What would be the I won't do that. They wouldn't ask you that on the exam, so I won't do that. That's a little thinking too far ahead. That's okay. So again, think about units. Consider everything we've done today. If you can do these problems with relative ease, I see no reason why you can't do well on the exam on Thursday. I may post another video Wednesday night, so be on the lookout for that. Might be helpful to your studying endeavors. Other than that, have a great week. I will see you guys next Saturday for might be the last recording of the year.